All right, so our next example is for a throttling valve. Okay, a throttling valve is a simple device intended to lower the pressure of a fluid as it passes through it. It's a simple device. It's usually either an obstruction in the tube. Um, Perhaps it could actually be a valve that's mostly closed, or in some cases, it's just a long, thin tube that that the pressure drop could be substantial. Just from the effects of friction with the walls. So we're going to dissect the problem a little bit. So we have R134A. Um, Enters the device at 800 kPa. And at 25 degrees C. Okay, it's throttled adiabatically. So there's no heat exchange. And it's throttled to a temperature of negative 20 degrees C. So and we're asked to find the output pressure, the outlet pressure, and the specific internal energy at the outlet. All right, so here's the energy balance. If you ever get stuck on any of these problems, writing the energy balance is a good first step. So it's a steady device. Okay. And so the energy, expanding a little bit on the energy balance, we get the energy coming in via being carried via mass plus work plus heat has got to be equal to the energy leaving via mass, work, and heat. All right, so it's adiabatic, so I can get rid of those terms immediately. I can look at the device and see that there's no work output. There's no way for work to exit or enter the device, so those terms come to cancel out. The work and the heat terms both cancel out. Now the mass flow rate can cancel out of both sides because it multiplies both sides of the equation. So I get a pretty simple energy balance of just the specific energy carried via mass is equal on both sides. All right, so we can expand these theta terms. All right, just by observation, I can tell that the elevation is not going to change appreciably. And then by assumption, the kinetic energy, the change in kinetic energy is going to be negligible. All right. Now that's an assumption. And it's more or less valid depending on the situation. For your purposes, if I don't mention a velocity anywhere in the problem, that's going to be the change in kinetic energy is going to be negligible. I will on quizzes or on exams and stuff like that, I'll be explicit about that. I'll make sure that you're not having to go out on a limb and make this assumption. Okay. So the energy balance simplifies just to the fact that the enthalpy does not change across the device. But we know the temperature changes, so there's got to be some. The state does change, but it does so at a constant enthalpy. All right. So the question is to find P2. what do I know about state 2? I know the temperature. And the only other piece of information I have about state 2 is that its enthalpy is going to be equal to the enthalpy at state 1. I don't yet know that, but I do have 2 intrinsic properties that I could use to calculate the enthalpy at state 1. So it's going to be the enthalpy at state 1 is the enthalpy as a function of pressure and temperature. And so H1, if I plug it in my calculator, so now I know what to plug in here for my second independent intrinsic property. So my pressure at state 2 comes out to 133 kPa. So the pressure dropped from 800 kPa down to 133 kPa. Second part of the problem is to find the internal energy, and that's pretty trivial, so it's going to be the same 2 intrinsic properties. And so that comes to that's the extent of what I'm being asked. But so what's going on here? These devices are a little bit confusing. But so where did the energy come from? How exactly did the energy exchange work? So if I look at enthalpy, I can break it down into its, if you remember, we can tear this apart and expand it just a little bit further. So what this means is that the pressure plus the flow work, the internal energy plus the flow work at the entrance has got to be equal to the internal energy plus the flow work at the exit. So what we're going to do is we're going to exchange the internal energy for flow work. Even though the pressure decreases, it's got to be made up for by a greater increase in the specific volume is what happens. So just to illustrate that, I'm going to write out these quantities. So U1, just like H1, is going to be the internal energy so U1 comes out to be all right. All right, so I've got everything I need to calculate the enthalpy, or this expansion of the enthalpy on the left-hand side. Now on the right-hand side, I got U2 already. I have P2 already, so now I just need V2, the specific volume. And again, just like P2 and U2, I can use those same independent intrinsic properties. And so on the left-hand side, I got U1. Plus the flow work, the product of pressure and specific volume. And then on the right-hand side, okay, and then so the product of these two quantities so I exchanged. It's a little bit complicated, right? My internal energy dropped, so as a consequence, my flow work had to go up. However, the pressure dropped, so intuitively you would have thought that the flow work had decreased, but it was made up for by about a 50-fold increase. Is it 50? Yeah, or maybe about a 550 or 500 fold increase in the um, specific volume. So the expansion of the fluid ultimately increases the flow work as a consequence of lowering the internal energy. So the interplay between the variables there is a little bit tricky because it's not really intuitive, because both the pressure and internal energy drop, but the expansion of the fluid makes up for it. That's where the energy winds up, that's where the energy conversion winds up being sort of felt.